Yes, good morning, everyone. Okay, so we're going to have a look at point-to-point interference modeling. I'm going to treat it simplistically. Right, so I'll quickly go through the microwave parameters, not as you see them, but as we need them. So the basic parameters: antennas, channel plans, net filter discrimination, link budget calculations, interference, and frequency. We won't do so much frequency assignment because once you've done interference, the frequency assignment is pretty inherent in it anyway. Okay. So before starting to do point-to-point systems with the ICS Telecom product or HTZ Warfare, if you're using it, the first thing you need to do is set up the preferences. Okay, so preferences in the computer, or the preferences for the environment you're working on in ICS Telecom, is Files, Preferences. Okay, so the ones that we are interested in for point-to-point is, first of all, the antennas. Mechanical tilt. Point-to-point systems mechanically tilt their antennas. They don't electronically tilt their antennas. So mechanical tilt needs to be used. Electronic tilt would tilt them 360 degrees down, and that's not the case in mechanical tilting. The back lobe goes up. So it needs to be mechanical tilt. And next thing is the interference over here on the right-hand side of the preferences. In most cases, people don't use automatic power control, so no microwave automatic power control. Certainly in UK, automatic power control isn't used. So we've got change microwave color if conflict. So that's just, it changes the color of the path between the line between the microwave systems if there is a conflict. And then we come down to some important ones. Okay, minimum co-site distance. Okay, so this is the distance between sites that are considered co-site. This is for things like self-interference rejection, which is the next field down. So if you've got a site with, say, 2 towers and they're only 20 meters apart, you may turn around and say, right, we want a minimum co-site distance of 20, 30 meters to make sure you pick it up. And then the self-interference rejection is the amount of rejection between antennas that are co-sited. There may be different heights and so on, but it's a general across the board antenna loss between the systems. So I'm going to stuff a 60 in there. There is an ITUR recommendation that describes how to calculate the coupling, on-site coupling between antennas. I can't offhand remember which number it is, but there certainly is an ITU one. And then the next thing that is important is how we're going to deal with the interference, co-adjacent and whatever. So there are 2 methods here. One is IRF from the TS and RIF are a power spectral density, and a RIF is a selectivity curves or shapes. Or you can get IRF from an NFD. So this is the net filter discrimination between system A and system B, and between system B and system A, and between system A and system A, and it's a huge set of, it's a huge matrix of information. And in some cases they are published, in some cases they're not. ETSI have published a whole lot of NFD information, and that can be selected if you want. So where do you put that information? So that information, if you are putting the power spectral densities and the selectivities, if you look in your ICS Telecom directory, so ICS Telecom is usually installed on C:, ATDI, and okay, I've got lots of versions of ICS Telecom because I'm always testing them and whatever. So we'll go to ICS Telecom EV, and the field that you want, or the subdirectory you want, is base. This is where all the base information tends to be stored. And there are two in here. There is TSR, and here are all the RIFs and TSs. You can see this is a 1.4 gigahertz, 1 megahertz, 2.1 megahertz RIF, and a 2 TS, and there are a whole lot in there. So that's where you put the RIFs and TSs. And if you've got net filter discrimination information, you put it in. You can see I've only got a couple in under NFD, at which point they need to be numbered so that you've got the transmitter and the receiver NFD. Right, so let's go back to the presentation. So we've gone through this mechanical tilt, automatic power control, colors, distance between sites, and the locations. And there are the locations. So you'll get a copy of this presentation from Sarah after the event. So if you need to look this up, you can use this to look it up, and it shows where these locations are. And so what does a TS and RIF file look like? Well, they are, you can open them in Notepad, and here I've got a TS file and a RIF file that have been opened in Notepad, and you can see that the first sort of 5 or 6 lines is just general information. Obviously, you need to give it a name and some information. The important bits begin about halfway down where it says 15. So it says that there are 15 values in this file, or 15 values that need to be picked up. And then there is the frequency offset versus the power spectral density level on the right for the TS file, and for the RIF, it's very similar, frequency offset and the selectivity. Now, obviously, if you are co-channel or 0 megahertz off, you expect all the power to be at around that point, and conversely, you also expect all the front end filter is open at that point, so all the signal will come in to it. There's no need to worry about the fact that one signal may be wider bandwidth than another or whatever. That is all taken account of in the NFD type calculations. So if you want to explore the TSs and RIFs, if you go to ICS Telecom, and I'll close the preferences here, tools, here you can go TS RIF mask, at which point you can load a TS and RIF. I haven't got any at that location, so C, ATDI, EV, base, TSR. So here we are. I'm going to go for a 1.4 megahertz, 3.5 megahertz bandwidth, or 2.3 gigahertz, 3.5 megahertz bandwidth, and I'll go for 2.3 and a 14 megahertz bandwidth. And if I calculate, you can see here that we've got a narrow band transmitter, which is the blue, power spectral density. We've got a 14 megahertz wide receiver, which is the orange, and the cumulative of the two is the red, which is the net filter discrimination. And it will automatically calculate the net filter discrimination from that information. If you have got NFDs to put in, you can't edit the NFDs because they are not an ASCII grid, they're in binary, but you can import NFDs directly. So there is an import text under the Tools IRF mask, and this is where you can view NFDs. So if I load an NFD, and you can see there are no NFDs in there, but if I go to the subdirectory NFD, here are the NFDs, and so I'm going to look at a 7G, it looks like 8E1 versus a 7G 8E1, and there is the NFD. So this is two systems very similar, and here are the NFD values that have been calculated out. So if I wanted to, if you've got the NFD values, you can import it as a text, which is a delta frequency offset and the IRF value or the NFD value. Or if you've got only 2 or 3 values, you can use the shortcut on the right hand side and input it, and it will automatically interpolate it out to the given NFD mask, and that you can then save them. Okay, so that's the NFDs, and I'll show you how we're going to use those in a minute. So going back to the presentation, which is not that screen, it's that screen. So NFDs, so as I said, it's either it transmits power spectral density or a receive selectivity, or you can import it directly as an NFD. So the other piece of information is a frequency plans or channel plans. So we can do a channel plan. Again, this is another set of information that is stored locally to ICS Telecom. So again, going back to ICS Telecom, all the things that are stored locally are database library. And you can see here we've got a set of TXRX parameters, an equipment database, an antenna database, over and above the ones that we already use. Feeders, frequency plan, bands, groups, site, user. So there are a whole lot of databases or data sets in here. So I'm going to look at frequency plan, and you can see there are two. There's a list, so that shows you what frequency plans are available, and you can double click on them, and there is a frequency plan. And if there are frequencies that you aren't allowed to use in the frequency plan, you can select them, and you can say not available. It's very easy. So that is that information. And to get that information in, if you go to database, library, frequency plan, there is an import ASCII file. And it says the format of it's a comma delimited file, so it's a frequency, a bandwidth, a parity, which is high, low, not used. I've forgotten what U and D stands for, probably something. A footnote of some sort, a mode, i.e. whether it's TXRX or whether it's TX only or whether it's RX only, and a flag of whether it's available, not available, or an intermod or something like that. And so you can browse, and if I go to live projects, webinar, point-to-point interference, here we are. I've got some 25 gigahertz channel plans here, and there is a 7 megahertz one here. And if I go edit, you could see it is a straight ASCII file. What I did is I put this together in Excel and exported it as a comma delimited file. So I've got frequency, band, channel number, bandwidth, parity, footnote, so it's ITU 478 is the one that this one comes from, mode, etc., as an ASCII file, and that will import, if I go OK, imported 128 channels, and so I can then go to database, library, frequency plan, list, and lo and behold, there is a 25 gigahertz, 7 megahertz channel plan and 2 times 64 channels, because it's FDD system. So we can use that later for frequency planning and assignments and so on. Right. Okay, so we've now got NFDs and we've got frequency plans into our into ICS Telecom. Next thing is the radio propagation models and the settings to do with those. Okay, so for point-to-point systems, generally ITUR 452 is used. So let's go and look at the propagation models. Tool, propagation models, settings, okay, so here's 452.16. So this is, there are 2 452 models in here. 452.14 is the old one based on the Daegu construction, i.e. 525, 526, 11, and 452.16 is the one based on 525, 526, 13, which is a Bullington construction. So actually it's quite a slow propagation model as propagation models go, because actually it has to do the profile 3 times under different conditions and then combine them together. So if we select that, the following menu will come up. Okay, so what does this mean? So we've got our clutter types down the left-hand side and the clutter codes if we've got clutter loaded. Obviously, if we haven't got clutter loaded, you can't use this. And there are 2 sets of profile heights, nominal heights. So if one imagines a profile from pixel 1 to pixel n, the clutter in the first clutter in the profile height section, the first one, is used. That adds clutter height to the terrain height from pixels 2 to n-1. In other words, it will be diffracting over the terrain plus clutter height if there is diffraction going on. If one selects the default 452, you will see that the value in there is 0. In fact, there is no mid-path clutter, as it's called, taken into account in the 452 calculation. But if you wish to take it into account, you just have to put a height in there. The only clutter that is taken into account is the end of path or terminal loss clutter. So there could be terminal loss clutter in front of the transmitter, or there could be terminal loss clutter in front of the receiver. And what this is again the height of the clutter, and the next field on the nominal distance is the nominal distance the receiver or transmitter is away from that clutter. And so if your antenna height is below that clutter layer, clutter height, it will assume that it is whatever distance away from that clutter it is, and it will do a diffraction down into the clutter. Now, if your antenna height is higher than the nominal height, so for instance, if we had a receiver in an open area and the antenna height was 4 meters or above, no terminal clutter loss would be applied. In other words, if your antenna is higher than the clutter height of the particular pixel that it is going into, no clutter loss will be applied to the system. So that's worth knowing. So if you don't want to take clutter loss or anything into account, just put a number in there that's below your antenna heights, and it will always not be taken into account. Close. Right, so that's the basic clutter information and 452 settings. When you select 452.16, it will automatically select in the top section the correct diffraction and subpath geometry. Do not change these, because if you change those, you won't be using 452.16. Use the default settings. Okay, so the next things we need to take into account is obviously earth curvature, and generally point-to-point is done on an earth curvature of 4/3, which equates to about 8,500 kilometers. If you wish to take it to a different K factor, there is a calculator here that will allow you to say what K factor and what earth radius. So if we want a K factor of 1, the earth radius is 6,371, in which case put 6,371 in the earth radiuses. There is a different earth radius for land and sea. So yeah, if you want to use it. Right. The next thing is percentage time. So the first one here is the percentage of time for the wanted signal. So we are going to be calculating a median field strength, so for 50% of time. If you tick this box here, just to the right of the variability, it says variability point-to-point unwanted signal. So this is the unwanted signal coming in. And if we are predicting or we want our unwanted systems to work for 99.99% of the time, obviously our unwanted signal shouldn't be there for more than 0.01% of time. If it is 5 nines availability, you want 0.001% time in there. Okay, so that's the basic settings for 452 point-to-point systems. It is worth mentioning that certainly in the UK environment, if the links Fresnel zone is intruded into, Ofcom are unlikely to license it. So it's worth making sure that the Fresnel zones are clear. Now, finally, there's one other little piece of information that 452 needs, and that is something called the zones, or whether it's a coastal, inland, or sea zones. So this can be computed, and if you've got coastal areas, you can compute it. There is a way of doing it. I'm not going to cover that now, but I have a coastal definition here called UK zones, and you need to load that as an RFL file, which is a compressed clutter file to all intents and purposes. And I need to use the ITU zone sets. So this needs to be ticked, use ITU zones for the 452 and in fact the 1812 models. and actually you can see underneath the blues and whatever colours come up of the different areas. So that now is the 452 setting for predicting point-to-point microwave systems. So at this point we could save it. There are a couple of other parameters we need to look at, so let's go to them first and then we'll save. Close, close. So we've got our propagation model done. Go back to the, so going back, so that is the setting of the 452 model. So one last set of settings that need to be done are the general settings. So we've got the limit distance, 100 kilometers, and isotropic under, so going back to telecom. So if you go up to the top under settings, I'm sure you're all very familiar with this. You've got the threshold levels, that's just threshold levels, wouldn't worry about it for point-to-point. This limit distance. So this is important in that if you've got interferers more than 100 kilometers away, in this case it will ignore them. So you need to make sure that your limit distance will pick up all the point-to-point links or all the possible interferers that are that might cause you interference. So that is important. Under thresholds, generally microwave systems work isotropic. So if you tick the isotropic at this point here, and now we have set up the preferences, we have set up the settings, we have set up the propagation model, we can now say File, Save, Parameter. And I now have a propagation model. I have a complete set of settings that are suitable for point-to-point set modeling within ICS Telecom. So if I save that, do I want to replace it? Yes. Update project. Do I want, when I next load this project, do I want to use these set of propagation models, preferences, settings, etc.? Yes. So it will update it. So next time you load this project, the propagation models, the preferences, and the settings that we've just gone through will all come up as we've just set them. Okay. So settings stored in the PRM file. So great. Okay. So we're going to do, I'm going to do a very simplistic link. So going again back to ICS Telecom. So we'll do map, 2D display, DEM display only. So I don't know whether you can see on your screens, but what I have produced here is a smooth earth. There is no terrain. There's a terrain 1 meter high. There is in fact no clutter. There's nothing in the way, no features or anything. And this is how I always start doing my projects when I am trying to develop a method or something like that, or just to double check what is going on. I always do it on smooth earth in a way that I can see exactly what is going on. So if I go File, Load, EWF, I have 2 microwave links, and lo and behold, we have 2 microwave links. I previously did some interference webinars. I used the same method, in fact, exactly the same area for doing those, and that shows you how to make a smooth area if you want to do this. So if we look at those microwave links, and we just look at them, as you can see, it is completely smooth earth, and they're well away. The Fresnel zones are well clear. etc. So that's great. Close. So let's have a quick look at, I think we're into parameters next. So we've done that. We're going to look at the parameters of the microwave links. So let's look at the parameters. Microwave link list, right mouse click, parameters. Okay, so here is the parameters. I am not going to go through everything here. I am sure all of you are very well familiar with the transmit powers and the antenna heights and the selectivities, and etc., and the frequencies. What I am going to go through is these bits. Here we go. So the first one is the frequency plan. So up the top here, we've got a frequency plan. So you can select the frequency plan for this particular equipment. So this system I know is 25 gigahertz and it is a 28 megahertz channel spacing. So there is the 28 megahertz channel spacing. It is worth putting in the diplex spacing, i.e. the difference between the uplink and downlink frequencies if it is FDD. The reason this needs to be put in is that because a lot of systems nowadays are becoming TDD and only use one frequency in both directions, and it all gets a bit complicated then. So spacing is a useful thing to put in there. Obviously, the rest of the information here is very standard, threshold levels, KTBF, noise, whatever. Then we come down to the NFD TS RIF. And if you've got them populated, which I have, here we go, I can say, right, this is a 25G, 28 meg system, and I can select a power spectral density on the transmit side and a selectivity on the receive side, and those will be combined with other systems so that you can get good close frequency reuse. Okay. Radio antenna patterns. As you can see at the moment, I've got omnis in. I want lots of interference. I want to show you the interference, so I have put some omnis in. What we'll do in a minute is we might change the frequencies. Well, the frequencies are all the same at the moment, but I might change the frequencies back to all the same after we've done some frequency planning. And just show you that the antennas actually make a big difference. So we will come back to antennas and obviously site locations, and you can check if it's free space and the margins and everything at that point there. Okay, so that's the first link, and if I look at the second link, you can see that it is fairly similar, except it's got a 14 megahertz channel and a 14 megahertz NFD taken into account. And again, it has got omni antennas. So we've got these two links in, and what we'd expect if we look at the microwave list is actually, because I've been playing with it, it's not going to happen. Let me just do something. File, station list. So what I'm going to do here is make a global change, and I'm going to change everything to 25 gigahertz. So we know we're going to have lots and lots of interference because everything is on the same frequency. It is worth noting, actually, at this stage, that if you've got a whole lot of systems in there and you haven't added the NFDs and you haven't added the frequency plans, you can do it at this stage. So to do that, if you go to the station list as opposed to microwave link list, so we've got two links there, which is 4 stations, and you can see we've got the 4 stations here. So what we need to do is add the information to the stations. So under change technical, if you've got the NFD name, you can change all the NFDs at the same time. Okay, so this will change all NFDs or all stations that are activated at one time. So if you put the NFD name in there, it will just put it across the whole lot. You need to be careful doing this. Obviously, if you've got 3.5 meg, 14 meg, 28 meg, 56 meg systems in there, what you'll have to do is isolate each bandwidth, which you can do easily, and do them one bandwidth at a time, because the same NFD would not be applicable to all of them. So that's the NFD. And if you wanted to change the frequency plans to all of them, again, the same thing applies. If you use change CX here, you will see change frequency plan about 3/4 of the way down. So again, you put in the frequency plan name and you will change them all. So again, you mustn't obviously put a 14 meg frequency plan into a 28 meg bandwidth system. So you need to filter and be quite careful when doing that. Okay, so we have done the uplink, downlink spacings and the NFDs and whatever. So the next thing is the link budget. So we can do the link budget for these links, microwave link budget. Okay, there are lots of options here. So let's just go through them. So there are various methods of calculating worst months and the outage times, but generally ITUR 530 is used. Certainly Ofcom use ITUR 530 and use average annual reliability. You need to tick update receive location ticked, so that it will pick up the local refractivity for the locations on the map. So in this case, it's neg 116.12, but it will do it for each link. We're not going to modify any transmit powers or anything. And we also want to take into account rain, especially anything above 6 gigs, you need to take into account rain, and actually sometimes below 6 gigs. So there are two options here. It says no rain or ITU. ITU means that it's picked it up from the propagation model. So in fact, I've got an ITU, or it gives you an ITU or a UK rain rate map. I've got the UK rain rate map. So if I've selected ITU, it would have had 28 millimeters per hour in here, which is the general UK rain rate. But in fact, I've got 35.4, which comes from the UK rain rate model, not the ITU one. So that's set up under propagation. And so if we go OK, that will give you the margin, receive levels, whether it's line of sight, gains required. So you can see here, we could turn this down quite a lot, and it would be still okay. So, and the totals at the bottom are assuming that all those links are end-to-end connected to one another. So those are the total outages for all the links together. Close. So microwave link budgets. Okay, so the next thing to do is we need to do IRF, or we need to do interference calculation. Okay, so going back to telecom, microwave interference. Okay, so we've got interference, threshold degradation. This means we're going to degrade the microwave threshold levels. if one degrades microwave threshold levels, that means that the fade margin is being degraded. If the fade margin is being degraded, that means that the availability, which is proportional to the fade margin, even though it's exponential, is also being affected. So if you threshold degrade a system too far, the availability will go from 99.999 or 49s or 59s availability, and it will decrease down below it. That is threshold degradation. Alternatively, there is a C to I method, which is a CI, in which case there are two methods of doing it. And we'll just go to the presentation. So threshold degradation, let's look at this. So if we take the blue line, which says, if we take the blue line that says noise floor, and for instance, if we have an interference line, which is the bottom line, the red line, which is, say, has an I to N of 6 dBs, i.e. 6 dB below the noise floor, the effect on the noise floor is that it is degraded and the noise floor rises, and it will rise by, in this case, with a 6 dB I over N, by about 1 dB. So the noise floor has gone up by 1 dB, and therefore, because the signal to noise ratio for threshold is a constant, the threshold level has degraded by 1 dB. So you can see here, if we can imagine a signal up near the top of the picture being the wanted signal, because the threshold has degraded, the fade margin has decreased, therefore the availability has decreased. So if the system had been designed for 99.99% availability and the calculation was 99.9999999, yeah, close to the threshold level, that 1 dB may have pushed it over the top. Now, if it just pushes over the top, fine, but if it gets any worse, you need to start taking it into account. Alternatively, if you use the C to I method, which was the other method, you can do it in two methods. One is similar to the threshold degradation, which is the median wanted signal and an up-faded interference level for say 0.001% of time, and you need a C to I between the two of them. So, yep, okay, so that's one way of doing it. And alternatively, you can go the faded wanted signal, in which case it takes the threshold level for the wanted and a median interference level, which is the interference level for 50% of time. So those two calculations need to be done in theory for point-to-point systems. The problem you've got is if you've got actually much better signal than is needed for the link, and you do the faded to wanted threshold level, i.e. the bottom one, and a median interference level, you're actually protecting the link much better than you should be, because you're giving it much more C2I than it actually needs to operate. So I'm actually, I was always taught the threshold degradation method, but there are two methods in here. So going back to ICS Telecom, here we are. So we've got all stations microwave, and we now need to go to IRF. So if we use, there are lots of options here. So if we use the default or the old basic option, we can say, right, if it is co-channel. Now, what that means is if the transmitter is co-channel with the receiver frequencies, it is 0. If it is adjacent to the receiver frequencies, apply 20 dBs. So that would mean that if it was a frequency in the next door bandwidth, receiver bandwidth, apply 20, and if it was 2 times the bandwidth, apply 30, etc., etc. So if you've got a consistent system, you can use the mask quite happily. Alternatively, you can pick up IRF from, they're built into ICS Telecom, the ETSI or ITU or IE tables. If it recognizes the frequencies and the bandwidths, it can pick it up from those tables. And in fact, we've defined the IRF NFD mask, so we can, we're going to use that in this case. Alternatively, for co-channel and adjacent channel, you can apply the C over I locally to each radio. So if we look at ICS Telecom, if we look at the links, parameters, you'll see that here, there is a C over I requirement for co and adjacent. So if there's any more interference beyond adjacent channel, it is ignored. So that's a simplistic method of doing it. So going back to the interference calculation, microwave, interference, all stations, oak, and you come up with the following result. So we've got here link 1 from 1 to 2 is interfered, has a threshold degradation of 70 dBs. We can then zoom into it, and here we are. The interferer is 3, is a minus 16 dBi C to I, threshold degradation 69.84, and down below here you can see that the wanted signals are coming in at neg 40 and the unwanted signals coming in at neg 24. So obviously completely and utterly useless, wouldn't work at all. Now it's worth noting here that if you right mouse click on the interferers here, you can look at the link parameters from 1 to 2. You can look at the interferer parameters, i.e. what the interferer is doing. You can look at the link budget 1 to 2, and you can look at the profile from the unwanted into the wanted receiver. So you can start to analyze this quite extensively. So obviously that is a completely and utterly useless system and wouldn't work at all. So just going back to the presentation again. So we've looked at that, and we've looked at the, I'll leave you to look at this, but what I've done here is put together how the calculation is done, and what I've done here is shown you where the various angles are on the link. So we won't do that. So how does one select the frequency? Yeah.
Hi, just a very quick question on that before we move on. If we use directional antennas, how would that change the interference in the example that you've used? So that's if we use directional antennas.
I think probably the interference would go away, which is why I used omni antennas in the first place. Let me do a frequency assignment, then I'll come back and we'll change it back to 25 gigahertz on each link, and we'll put antennas in, because that actually solves the problem as well. So
Lovely,
we'll do a frequency assignment to solve the problem, then we'll do change the antennas to solve the problem. So a frequency assignment. There are lots of ways of doing frequency assignments. Right, so let's look at this simplistic thing here. One, we could do an assignment to everything that is on the map. So if we did this, you would select obviously we've selected a frequency plan for each system. Select frequency plan, fix spacing, and select IRF from NFD matrix, oak. Now, if we selected this, it would go off and it would frequency plan all the activated, in fact, let's do it. It will frequency plan all the activated stations and we would end up with no interference. So if I now do the interference calculations, interference, oak, hey, I've done something wrong somewhere. Microwave assignment, threshold degradation. What have I done wrong? Fixed spacing, number of passes. Let's put number of passes 3. IRF, NFD matrix, oak. Yeah, that's better. Right, I didn't put enough passes in, so it just went round once and stopped. Right, so if I now do microwave interference, it will come up with no threshold degradation found. Now, that process will work for network-wide frequency planning. Now, most of the time, there isn't any network-wide frequency planning. Most of the time, you've only got 2 or 3 links to do. So the way to do that, and you need to take account of all the other links. So the way to do that would be to deactivate all links that are fixed. So draw a square around them, stations, deactivate stations. So that link is fixed, and we can now then go and frequency plan using this method the links that are activated. I'm not going to do it because I want to do it another way. Draw a rectangle, stations, activate all stations. Alternatively, we can do it one at a time. So we could go to microwave link list. So here's the microwave link list. And I want to frequency plan link 2. Okay, here we are. Check frequency list map. So this will check all the frequencies for links that are on the map. You can do it from link map to database or bands map to database or whatever. So we're going to use map to map. Here we go. Right. So you can see I've got a whole lot of frequencies in here. This is a 14 megahertz channel bandwidth system. So I need to select it from plan. So here we are, 14 megahertz, and we need to select those frequencies that are on the plan. So there we are. Those are the ones we know that are available, for instance. And if we wanted to add extra ones, we could say we could add that one and that one. Basic Windows function, and we could select them. And from plan. Right, so we just need to get rid of the other. I should have set them all to 0 first, but I'm just going to quickly whip down and change these to 0 because I haven't actually selected enough frequencies to fill it all, to overwrite it all. Right, so there we go. So they're the frequencies that are available for this link, and I can go OK, and it will come up with the following result. Okay, so what it is saying is if you select the first frequencies at the top here, 25564 and 24556, you're going to cause no interference. If you choose the third one down, 2592 and 24584, you're going to cause interference into 2 stations. So you can now go through all the frequencies and say, right, which one do I want to assign? So for instance, in this case, I want to assign the third one because I want to cause some interference because I'm that way inclined. So there we are. I've assigned it that frequency, at which point it now recalculates the whole lot and it will return, here we are, link 4 to 3 has a threshold degradation of 61 dBs from station 1. And the wanted signal is neg 38 and the unwanted signal is neg 36. Not surprising. So that's the wrong one. So we can now restart the whole thing and go, right, I want to select the first channel. And in that case, we end up with no degradation, at which point I can go close and the frequency has been assigned. So that is the quick way of, or that is the best way of doing individual stations when you've got a network to take account of. Now, one of the things we saw there was that the interference was due to, we've now frequency planned it out of the way. So now let's do it with antennas. So if I go to station list, change technical, change it all back to 25 gigahertz. So 25 gigahertz, close, and if we look at microwave interference, you can see it's all interfered, 70 odd dBs of threshold degradation. And if I now apply an antenna to the systems, so what I'm going to do is I'm going to apply a general antenna across all of them. So I'm going to apply a 3D file, and I'm going to select an antenna, and is Andrews Corporation, and I'm going to select a 2.5, 240, I think that's the right frequency, yes, 240 antenna oak. So I'm going to apply that to all the stations oak, modify no. So I have now applied that antenna to all the stations that were activated. So let's have a look at the parameters. Okay, so you can see we've got an antenna. Next thing I need to do is just make sure the antennas are orientated. So let's just orientate. So microwave options, orientate antennas. And now if we do microwave interference, so we've now got antenna discrimination in, you can see we've got a little bit of interference, 1 dB threshold degradation on one link from 1 to 2. So the interference is 2. So we've got a wanted signal of neg 40 dBm and an unwanted signal of neg 99 dBm, which is causing 1.12 dB threshold degradation. Now, this might be perfectly acceptable, and certainly when Ofcom assign you frequencies, there's probably 2 or 3 dBs worth of fat in the bottom of it so that they can degrade your performance by 2 or 3 dBs without actually having to think too hard about things. Right, I've realized I've gone on a bit. I've got one other thing that needs to be covered. So we've gone multi-point, last thing is multi-point interference. So we've got the systems in like this. Now, if we had another system that was adjacent channel or co-channel or whatever, and it was a completely unknown system. So here we go. I am going to put in a radar. So we'll put in a radar, and it's got a pattern which is going to be omni. Going to go round and round in circles as they normally do. and it's got a huge transmit power, and it's 25 gigs as well, not there are. So there we've got a radar. How does one do a calculation of radar interference into these systems? Well, you put the radar in as a station, but you can't use the microwave interference because it only deals with microwave stations. What you have to do is use the multi-point interference. Here we are. And the one you want is global interference. So this is the one we can take other things into account. So if we wanted to do exactly as we have been doing, we could do microwave to microwave like that, select the IRF, select it from matrix, and it will produce no interference. Fantastic. So now if we do multi-point interference, global interference, and we can now do microwave into station and station into microwave, oak, and hang on a second, parameters. Can I just change that back to a station and see if that works? Multi-point interference, global interference, oak. The antennas are too good. It's not seeing it. I didn't try this in advance, which was silly. What have I got? Antennas, general, 25,000 watts. Right, let's do this. Station list. Change CX. No, wrong one. Change antennas. Omni, do change. Oak. No. Okay, so now if we go multi-point interference, global interference, oak. I've done something somewhere. Anyway, rotten ending up on something that's not working. Oak, why isn't it working? Global interference. What should be happening and isn't is that the station should be interfering with microwave and the microwave should be interfering with the station. And I've obviously got some parameters not set up right somewhere. But this is how you deal with the case where you're not dealing with the same sorts of systems. You're dealing with adjacent systems in adjacent bands and things like that. You can use the multi-point interference. Now, I realize I've now chatted on for about an hour, so I'm going to call it a day there, and I shall just fiddle with this and see if I can make it work. And are there any questions? Could Ms. Kirkman explain again the meaning of the spacing megahertz and microwave link parameter? Did you change the point-to-point? Yes, I did change the point-to-point. The Andrew you used was very directive. Yes, it was. At 25 gigahertz, the quite small antennas make quite directive antennas. If we've been playing around at 4 or 6 or 2 gigahertz, it would have been a much wider antenna. But you know, that was only a I think I selected a 1.2 meter antenna, yeah, it's quite directive. Will I put him? I will put it to there.
There's lots of questions.
A lot of questions. Yes, I'm seeing them coming up. Hang on a second. Let me just drag them across where I could see them bigger. So yes, I did change the antenna pattern. Andrews was used. Yes, it was very directive. So if we look at it again, file station list, antenna, 3D file, select antenna, antenna corporation. I think it was a 1.2 HP X 240E. 25. I can't find the 240. Sorry, I'd set that up beforehand so I could easily get to it. I can't find it again now. I can't find which one it was. Yes, but at those frequencies, it is very directive. Could you explain the meaning of the parameter spacing megahertz? Yes, certainly. Right, so we're going back to close microwave link list parameters.
So the question here is for his explanation of the meaning of the parameter spacing megahertz in a microwave link parameters. For those
okay, so if you've got an FDD microwave link, there is a spacing between the transmit and receive frequencies, or the diplexer spacing, or it's not the diplexer spacing, but it's the spacing between the spacing between channel 1 and channel 1 prime, or channel 1 prime and 1, and that is the spacing that needs to go in there. Otherwise, you'll end up with a single frequency being assigned. So I change. What if you don't have an NFD for any equipment? Yep, very good question. I have found this problem a lot. Certainly, Etsy have a lot of the NFDs or information if you are playing with microwave equipment. If not, there is a method that is in the harmonization calculation methods within Europe that allows you to define the masks from the modulation type, the bandwidth, and I think that's about it. Those two pieces of information, and you can derive it from that. In fact, if you have a copy, if you're using ICS Manager, and I'll just flick it up for you in a second. I need ICS Manager, ATDI software. I think this is the right one. Yep. So if you have ICS Manager, so this is the ATDI database for that goes in front of ICS Telecom HTZ Warfare and is the management tool. It actually has a calculator in there that does or pretty well produces the net frequency discriminations automatically. So here we are. Here is a record for a microwave system, and if I go to the parameters and go to I think system, select, cancel, edit, go to system. Yes, here we are. It's got an ability here. So you say, right, select the method with spectral efficiency class from HCM, state the method, so it is a 4QAM system, and based on the bandwidth and the fact that you've said it has a spectral class from HCM and it's based on 4QAM, that would be the power spectral density and the receiver rejection for that particular microwave link. So that's based on the spectral class efficiency of HCM. So that's built into the ICS Manager product, not into the ICS Telecom one, because obviously it's a management thing. I was asking because radar wasn't seeing. I was asking, yeah, I don't know why the radar's not seeing it at the moment, but I need to sort it out. I think antenna was selected from 2.5 instead of 25 gigahertz. gigahertz. No, I think it was 25 gigahertz because it was a 240. And if my memory is correct, that is 25 gigahertz. Let me just check. I have the infamous Andrews catalog in front of me, and 25 gigahertz is a 12, 14, 18, 17, here we are, 21 to 23 is a 220. Did I select 220 or 240? My catalogue's old, so I'm not certain if I got the right one.
Okay, Nick, just
here
because
are, 21 to 26. Here you are, yeah, a 240A, a VFP 1.2 240A, has 35.9 dB gain, and it doesn't give me a doesn't give me a beam width, but yeah. So I did select a 25 gig antenna. What are the critical parameters to fill out for IRF from ETSI setting? ETSI setting, ETSI. Don't quite understand that one. What are the critical parameters to fill out to use for IRF? I think, if my memory is correct, ETSI have got a whole lot of the IRF tables. In other words, a 2G 14 meg bandwidth system versus a 2G 34 meg system. They've got a whole lot of tables published in those, and all the published tables are in ICS Telecom. So what you'd have to do is, when you're doing the microwave interference calculation under the IRF here, you select IRF from ETSI ITU tables. So that will automatically apply net filter discrimination between the various systems, as long as it can recognize what systems they are. In other words, it is within the right frequency band, in the right channel, with the right bandwidths.
Okay, Nick, is that us finished with the questions? Yeah, that's great. Thanks.
I think so.
Okay, we have gone over time here, so I'm conscious that we're running about half an hour over. Thanks for joining us, everyone, today. Just as a very, very quick follow-up from today's event, you will receive a link for a survey. If I could ask you to complete the survey, we'd be most grateful. It just helps us develop subjects for future events. I'll also be sending you a separate email, which will include invites for our future events. So we have a webinar scheduled for April, and also a user group meeting in May that you'll receive an invitation for today. You'll also receive in that mailing a recording link from today's events, handouts and slides. Okay, I'd just like to take this opportunity to thank you, Nick, for taking the time and running today's events. Thank you everyone else for attending, and wishing you all a great weekend.